Let us start our next portion of our chapter, which is the calculation of shear stress of different type of bending itself. Now, in the last class we have discussed what is the shear center of the or center of the curvature itself. Shear center or center of curvature, both two names of a particular phenomenon here. We considered the bending of beams subjected to, just 1 second. Now, in the previous section, we considered the bending of the beam subjected to pure bending moments itself. In practice, the beam carries a load which are transferred to the axis of the beam. Means, you see, this is a beam, which is cantilever in nature. Is one end, right hand is free, and left hand is embedded in the wall itself, and the load is acting upwards at the point at the rightmost point at the end point of the right side of the beam itself. This beam is transverse in nature, but since it is not going through the longitudinal axis of the beam, it is not perpendicular to the longitudinal axis of the beam, it is away from it. So, it creates not only normal forces due to the flexure, but also transverse shear forces in any section itself. So, line of action here, if we take an arbitrary section of the beam like this, where OYZ is the coordinate axis itself, and O is phi passing through the centroid, and external load P is away from the y-axis by an amount E is equal to by an amount E. Now, in general, this will cause both bending and twisting. Now, what we have told just now, this is OX is the central axis, hence it is acting normal to the plane of the paper or plane of the computer, and OJ and OZ are the principal area of the section itself. Let the load be parallel to one of the principal axes. This is one principal axis, this is one principal axis. If the load P is parallel to one of the principal axes, that is parallel to the axis OY itself. And each load can be treated separately if there is a multiple load is there. This load is generally will at any section will cause a normal stress sigma x due to flexure. This is a normal stress. Any section will create a normal stress, which is equal to sigma x. This is due to flexure. It is called flexural stress also. Shear stress tau xy and tau xz means shear stress along in the plane x into z and x into y and x into z itself. X into y and x into z itself. And with the due to the transverse nature of the loading and shear stress tau xy, tau xz due to torsional nature. Shear stress is due as the transverse nature of loading means, and shear stress are due to torsion itself. This is creating a torsion as well as it is creating a transverse means an axis normal to the axis longitudinal axis of the beam along any section of the beam itself. That is transverse in nature. Now, to obtain solution, what is sigma x is equal to load multiplied by the length itself. P is the load. It is a particular section here, which is away by a section x here. So at this end, at this position is L into x. P multiplied by L into x to y. That is the distance of the neutral axis from the beam divided by ij. For sigma y, sigma z, tau yz, these are all equal to 0. Only sigma x is equal to perhaps have a meaning. This is defined as self-dependent assumption itself. The value of tau x and tau xj are to be determined with the equation of equilibrium and compatibility condition itself. The value of sigma z is given above is derived according to the flexure formula of the previous section. The determination of tau xy and tau xz for a general cross-section can be quite complex, but we are not going through it. We should try to determine this. We should not try to determine this itself. So one important point we have to note it, as the float P, in addition to the causing bending, will also twist the beam. But P can be applied at such a distance from the centroid that twisting does not occur. For a section with the symmetry, the load has to be along the axis of the symmetry and to avoid twisting. So what is thing? We know we have to maintain symmetry and load has to apply along the axis of symmetry. So in that case only, there will be no twist. On the same condition, if a beam with a general cross section, the load will have to apply the distance E from the centroid EO. When the load P is parallel to the Z axis and a position can be established for which there is no rotation of the centroidal element of the cross section occurs. The point of intersection of these two lines of the bending force is of significance. This transverse force is applied at this moment. We can resolve into two components parallel to y-axis and z-axis, and do not produce rotation of the central elements in the cross section. This point defined as shear center of flexure or flexural center. See, center of flexure, shear center of flexure or flexural center itself. Now, in the last classes, we have derived this equation tau Sx and tau Sj, Sx or Xs is equal to Vy by Ty, etc. Vy divided by Ts multiplied by Iy into Ij, and into minus L into Iy, Iy into Qj minus Iz into Qy. Now, if we follow this equation here, if we determine go through this Newton problem, which is given like this, we have to determine the shear stress distribution of a channel section of a cantilever beam subject to load A, as shown. Also, locate the shear center of the section is here. Also, so what we have to do, the shear stress distribution and shear stress center to find the shear center of the beam of the section. Our section is the channel section like this, and load is the beam is cantilever fixed at left end and being loaded at the right end itself. But right load is not exactly on the beam itself, but of a projection of the beam. That reason I will explain afterwards. Now, if the channel is magnified to a certain extent and sides are placed over it, it will look like this. The width of the flange will be B, and B at the bottom at the top, and height of the wave is from H to H, from the center of the top, and B is also center of the wave, the right end of the wave itself. And this is our axis O, Y, Z, and our x-axis is normal to us. Our coordinate axis O, Y, Z is here, and our section is exactly symmetrical about the OZ as well as OY axis, both together itself. No, not only for OZ axis, but not from Y. And we will consider the sectional area over the thing as shown in the figure itself. It is away by the amount Y itself from the Z axis itself. And the thickness of the upper portion of the flange is equal to T1, and that of the lower portion of the flange is equal to T2 itself. Let OYZ be the principal axis so that IYX, YZ is equal to 0. So OYZ we have captured as principal axis means loads acting along this axis will be maximum or minimum, both are in tension or compression, not in shear. So here, as OZ is the axis of symmetry, so the IZ, the area moment inertia about this thing will be supposed to be 0. Now, from the earlier equation shown here, we are putting F is equal to minus F and put it here to eliminate the next one itself, because here the load was at the upper side here, upper direction. Here the load is at the lower direction, so we can say put it at minus F to use the same equation itself. So tau Sx becomes F Is into Iy into Iz multiplied by Iy into Is Iy into Is itself. Then tau xz f qz is not Is by Ij, because Ix Iy is cancelling each other from numerator, and f and Is and Iz into qz. Qz is the statical moment of area from s is equal to 0 to s is equal to s about the z axis itself. This is the static moment of the total area we have to find. So consider the top flange where T2, Ts is equal to T1, and the statical moment will be the area T1 multiplied by the length s. Whatever be the value at this moment, length is the s, the distance from the axis of rotation is equal to half h, that is h by 2. So T1 into s multiplied by h by 2. So thus, if you put the value of qz here, it will become tau x sx is equal to fsh divided by 2 into ij, where s stands is greater than equal to 0, means from end of this end, or less than equal to b, this up to this end. So this length is being considered from this end to the center of this wave itself. The shear stresses increases linearly here from s is equal to 0 and to s is equal to b. It is at 0, it is the minimum, it is at maximum at the b end. So for s in the vertical wave, Ts is equal to T2, and the statical moment is the moment of the shaded area about z axis. Here, S means the length of the in the vertical portion, where the thickness should be equal to T2. The statical moment is the moment of the shaded area in frequent itself. We have to consider the statical moment. Here we have to consider the moment of the upper plane. Here we have to consider the statical moment of this area, which will be exactly same on both sides itself. So how will you do it? We have to add this b width into T1, and as well with the width of this upper portion to T1, the distance from the axis of rotation is equal to h by 2 plus this portion of the wave itself, which is length h by 2 minus y, is total is h by 2 minus y is the distance, multiplied by thickness T2, multiplied by y, this y plus half of h by 2 into y, this y and half itself. It's the axis of rotation from here, y plus half of this level. This is the point here. And if you simplify and neglect this y into h by 2 minus y, this equation will form here h by square minus 4 into minus y square into T2. Thus, TSS is equal to f by 2 T2, I2 into ij is equal to b T1 into h. Thus, h square by 4 minus y square into T2. 1 second, please. Here, a tau xs is the f by 2 tau t into z, t2 into 2 into t2 z, b into h by h square minus 4 minus y square into t2. For y will vary from minus h by 2, means from this end, from here, which is minus side, because the oy is plus on the top side, is plus h by 2, this is minus h by 2. The shear varies the shear is here varying parabolical to s is equal to b and to s is equal to b plus h. Means s is equal to b means here, s is equal to b plus is here. Means shear force varies parabolically from this end to up to from this end here to this end here. So s in the horizontal flange, Ts by T1, and the statical moment will be T1 in the flange, the statical moment T1 by h plus 0 s minus b minus h. S is the length minus b this length minus h this length, means this length will also express multiplied by T1 multiplied by minus h by 2. H by 2 is the distance from here to this side itself. So this distance plus this distance, length and area and multiplied by distance is the statical moment of these two flanges, those flanges here, and we have got the statical moment of the flanges here. Thus, qz is equal to B into T into H by 2, and B must be, this is the QZ. This is the statical moment of both these flanges itself, which is equal to BH plus H square by 2 minus HS minus to T1. Now, if we put this value in the equation of tau x, it will become tau x here, which is there F into, it will become F by 2I it again, and this T1 will cancel each other, and BH square by 2 minus this. So, where S is equal to B into H plus 2B to S B plus H itself. The shear stress varies linearly when S is equal to B plus H, the height the shear stress varies linearly when S is equal to B plus 2H means 2H means this 2 plus 2 into this B and this B plus H, the right tip of the bottom flange, the shear is 0. The variation of the tau is also shown in here. The right tip of the bottom flange and right tip of the top flange, both the shear stress is 0, and it is varying in a regular fashion here. This shear stress distribution should be statically equivalent to applied shear stress F. It is equal so that it is to see that this is equal to F in magnitude on integrating tau ZX over the area of the section. The resultant of the stress in the top and bottom flange should cancel each other, and therefore there is no horizontal resultant itself. So integrating tau Z over the vertical wave itself, what we do, we are integrating from the two ends minus H by 2 to plus H by 2 tau Sx multiplied by thickness T multiplied by the height Ty to get the area of the force, which is equal to Fij, and we put the tau xs as integration of Bt1 H into Ty plus integration of H square by 4 minus Y square T2 into Ty. Now, if we integrate, we take this form F divided by 2I into H Bt1 H square, because we are taking the boundary condition minus H by 2 to plus H by 2, and thus, and here it will be H square into Y by 4 into T2, and H to the power 4 by 4 into T2. And if we put the value of my plus T by 2 and minus 2, take this form H cube by 4 minus H minus 2 by 12 T2. That it will again become equal to Pt1 H square plus T2 H cube by 6 multiplied by F by 2 into Ij. But we know that Ij is equal to Bt1 into H square by 4, Bt1 H square by 4 plus T2 H cube by 3 12. So this is equal to Ij reduced to Bt1, or this equation Bt1 I square by 2 plus T2 H square by 12 is there. Thus, minus V by 2 plus V by 2 is equal to tau xy into H by is equal to F itself. The resultant of tau x shade over the area is equal to F. In addition, it is the moment. Taking moment about the midpoint of the vertical wave, so M resultant of tau x in top flange multiplied by H by 2, plus resultant of tau x in bottom flange multiplied by H by 2. So we are taking moment of the forces here and here from the central itself. The two resultant of tau x in top, because they are same, H by 2, or average of tau x in top flanges into area into H by 2. So average become F, the force multiplied by the force with B into H divided by 4 into Ij multiplied by B into T1 into H by 2 itself, or 4 T square H square T1 divided by 4 Ij itself. And this must be equal to the moment of F about the same point. Since F must be at distance E2 from A2 from C such that F E2 is equal to F T square H square by T1 by 4 Ij. So E2, the distance of that, the point of application of the force is D square H square into T1 divided by 4 Ij. Substituting for Ij, we have this equation 3 D square H square into T1 divided by 3 BT Pt1 into H square plus T2 into H cube, or E3 3 B square by T1 6b into T1 plus T2 into H. Hence, shear stress is located at distance E2 from C itself. Let us go through another problem. Here we are determining, we are having a ring. It is not round, it is round, but it is open at one of its sides itself. Determining the shear stress distribution for this circular ring after being caused by shear force, locate the shear center itself. Same because we have to shear stress distribution like this from here, and where is the shear stress, and the force is applied here, causing a shear force here. The static moment of the cross section will be like this, but we have O as the center of the ring, and theta from the horizon is and we are considering a section of the beam from the free end to up to this end, which is this end is at an angle theta from the horizon itself, and we are having elemental length here, and which is having an elemental at a distance phi, and this element area is have an angle equal to d phi itself. R is the mean radius of the beam. R is the mean radius of the ring itself. R into d phi into t. R into d phi into t into r sine theta. What is that? R into d phi, the radius. This is this portion of the beam multiplied by thickness of the beam, and it is the angle theta, angle the r sine phi. R sine phi is the height of this beam from the axis of rotation itself. So the QZ for this section is equal to R, this length and volume of the section, cross section area of the section multiplied by it's the height distance from the center itself. So we are integrating the whole from 0 to theta, from here to theta itself. We'll have r square into t into 1 minus cos theta, because the integration of sine phi is equal to minus cos phi. And if we put the value of 0 and theta, then 1 by 1, and the boundary condition, one condition will be 1, another will be minus cos theta. So again, we can equal figure 3, but then we, as we know, the QZ, then IZ is equal to 0, and the vertical force tau xy f QZ divided by t into IZ itself equal to minus f by t into ij into r squared t into 1 minus cos theta itself, or ij is equal to pi r cube into 3 r I cube into t. Hence, f divided by pi r t is equal to 2 multiplied by 1 minus cos theta we replace r theta by this equation, and this equation given f divided by pi r t 1 minus cos theta. For theta is 180 degrees, because theta is equal to 0. So from this end, it will be one value, and this end it will be another value. Value will be equal to minus 2f pi r theta. From theta is equal to 0, it will be decreased and minus 2. This is exactly twice than the stresses at the right section. Distribution is shown in the figure 6.17p. Moment of the distribution is m equal to 0 to 2 pi x r d theta into t into r. So f by pi r t 0 to 2 pi r squared t into 1 minus cos theta d theta into minus 2 f r. It should be equal to the moment of the applied transverse force above O itself. Just 1 second. This should be equal to the moment of the applied transverse force F above 0. For F is F positive, the moment about O is negative, since it is derived from Z to Z plus. Hence, the force F must be applied at the shear center C, which is at a distance 2r from O. Let us discuss the shear center of two other sections. There is a section C here, and there is a section T, and there is a section L. The thin wall inverted T section, the distribution of shear stress with transverse shear will be as here, like this. Moment of the shear distribution center about the C is absolutely zero. Both these are the same. If you take a moment with both of them, it will balance each other. So this is the shear center or center of flexure of the beam itself for a section. And shear center C is the here is the same thing. There are the two line of shear stress itself. Both are cancelling each other if you take a moment. So add about the C. So C here, C is the shear center itself. And if we don't go through the apply your external force to the shear center, what will happen? This pen will bend, it will twist like this, will take this form like this. When beam is irregularly shaped, you have to find out the shear center and apply the external load to the center, or your beam will got twisted effect on the beam itself. So far, we are discussing the bending of beams which are initially straight. Now we'll study the bending of beams which are initially curved. We consider the case where bending takes place in the plane of curvature itself. It is possible when the beam section is symmetrical above the plane of curvature. First of all, what we are doing, which beams were initially straight. Now we'll find the beams are initially curved, and we find out the effect of the external force over it. We will consider the case where beam takes place in the place of curvature, takes place in the plane of curvature. That bending takes place in the plane of curvature means it is already curved. There is a particular plane over which is curved, and it will curve more or less after the action of external force, but in the same plane of curvature itself. When this is possible when the beam section is symmetrical about the plane of curvature. Then if you take a section of the beam, it will be exactly replica, both sides will be exactly respect the other, and symmetrical through the symmetrical will apply the bending moment to externally applied bending moment to make a symmetrical bending through the plane of curvature itself. Rho is the initial radius of curvature given here. This was the initial radius of curvature at the centroid of the beam itself, which is given by the rho here. Now, as in the case of straight beams, it is again assumed that the sections which are plane before bending remains plane after bending. Here is also doing thing. The section all everywhere remains plane before and after bending. It is not twisted or disturbed. As in the case of straight beam, as in the case of a straight beam, it is again assumed that sections which are plane before bending remains plane after bending. Okay. Consider an elemental length of curved beam. Here, what is that? An angle equal to d phi itself. We are taking an element length of the beam from here to from here. The in between angle here is half of the angle is equal to d phi from here. So let us take this element from F into A to from B to G. An elemental angle is equal to d phi itself. Owing to the moment M, bending moment M, let the angle owing to the bending moment M, let the section angle AB rotates through delta phi. Due to bending moment, it rotates delta phi itself and occupy this position, given as B dash and A dash. Initially, this portion was B and A. Now it has become B dash A dash. Okay. Here it is rod due to the external force. It is bent. This portion bent further. This portion reduced, drop down up to this point here. That angle increases from d phi to another, from d phi to another delta d phi. Now, the fibers above, first of all, the section rotates about the section NN. NN is the neutral axis. So you know there is no force acts in this line, and there is no increase or decrease in length of this line. So about this neutral axis, this bending takes place without affecting its length itself. So AB is going through the going to the point N of the neutral axis, and A dash B dash also going to the point N in the neutral axis. Thus, point N is not moving, but other portion above that it is compressing the fibers, and bottom portion is tensing, stretching the fibers itself. But any fibers along this N line, NN line or SN line, it is not stretching or contracting at all because it is on the neutral line itself. Now, let us consider another fiber at a distance y from the neutral axis itself. This unstretched length before the bending is r0 minus y into del phi. R0 minus y. So R0 minus y means somewhere here. R0 is the length of this neutral axis, I mean radius of the neutral axis. R0 minus means length somewhere here. The unstretched length before the bending was R0 minus y. The length was R0 minus y into d phi. Before the bending, this was the unstretched length. But the change in length due to the bending is now this thus becomes delta phi itself. It becomes y into delta phi. So as this angle is bent by angle delta phi and length is y, the angle bent by increases bending is equal to del y into delta phi delta. Noting that the moment is shown, this strain is here negative itself. Then epsilon x is minus y delta phi r into y delta phi itself. It is assumed that the quantity y remains unaltered during the process of bending itself. So, in the value of delta phi by del phi can be obtained from the figure 220 itself. This is the figure. It is shown that Sn means length of the neutral axis from here to the point of action of the bending itself. That is Sn is equal to r. R is the length from this point here to here. R multiplied by del phi plus the angle del phi, which was initially increased initially, plus delta into del phi, which was increased afterwards. So Sn will be now r phi delta y into phi into r. But this is remains same. But r is the constant of radius of the neutral axis after bending. Also, Sn is equal to Sn becomes equal to r0, means initial radius of the neutral axis multiplied by the del phi itself, r0 del phi. Hence, if we divide them together, as this portion del phi into phi into r divided by r0 del phi is bottom is equal to 1 itself, or del phi by or del phi into del phi plus del phi into del phi is equal to into by del phi to 1. So if we take the relative, del phi divided by del phi will be equal to r0 by r minus 1, or r0 1 by r minus 1 by r0 itself. This is the substitution equation 30. Substituting in equation 30 itself, this becomes r0 plus phi. This is del phi. If we r0 minus 1, we put it here. That is r. And no, first make r0 by r divided by this thing del phi minus del, then del phi minus 1. This one plus divided by del phi. Then r0 minus 1. This minus will take on right side. Then r0 minus r minus 1 r0, or 1 by r minus 1 by r0. Now, if we substitute in equation 30, that is equation 30, epsilon x will be delta 30 by delta r will become y by r0 minus 1 into r0, 1 by r minus 1 by r0 itself. Now, we assume that only delta x is acting and that delta y, delta z are not acting at all. This is similar to Bernoulli's-Euler's hypothesis for the bending of straight beams. On this assumption, we know a sigma x is equal to e minus e into y, r0 minus y into r0, 1 by R0 itself. This above expression brings out the main distinguishing feature of a curved beam. The value of y must be comparable with that of the R0. That is, beam must have a large curvature in which the dimension of the curvature of the beam are compatible to the radius of R0. On the other hand, the R0 is very small, by R0 is very small. So we can neglect it compared to y, then equation 32b becomes this equation becomes t into y by R0 divided by 1 by t into y into 1 by r by R0, where R0 may be equal to infinity, equation reduced to that of a single beam itself. Okay, let us finish here.